ENUS. In the vast expanse of the cosmos, within the constellation Bootes, lies a region so grand and empty that its scale defies imagination. This cosmic void could contain 1,000 galaxies like our Milky Way, with plenty of room to spare. It's not merely the vacuum between stars, or even the immense distances separating galaxies. This is a truly unique area where galaxies are simply absent. Scientists have named it the Bootes Void, and its discovery forever changed our understanding of how the universe is structured and what it should look like. We invite you to delve into this bottomless cosmic chasm, explore the few isolated galaxies that, for some unknown reason, found themselves within its boundaries, and realize how this colossal nothingness forces us to rethink everything we once considered immutable reality. Prepare for a journey. We are heading deep into the void. In 1977, astronomer Robert Kirshner aimed his telescope at the constellation Bootes and encountered absolute emptiness. He found no shimmering light from distant galaxies, no scattered star clusters, not even the tiniest particles of cosmic dust. Before him stretched only a silent nothingness, so boundless that it seemed as if light itself dissolved into this primordial blackness. Kirshner discovered something that, according to all existing models of the universe's structure at the time, should not have existed. It's crucial to understand why this discovery was so unsettling. When we gaze into the depths of space, we are accustomed to expecting galaxies everywhere. They should be uniformly distributed throughout cosmic space, like city lights viewed from an airplane at night. For a long time, we believed the universe possessed relative homogeneity. It was assumed that matter was distributed fairly evenly, and galaxies formed a cosmic web of light stretching in all directions. However, this particular region of space violently violated all established rules. Imagine this. If you could shrink our Milky Way galaxy to the size of a quarter and drop it into this colossal void, you would need to drop another 999 such quarters to even begin to fill this immense empty space. The Bootes Void stretches for 330 million light-years. This means that light, which travels at an astonishing 670 million miles per hour, takes 330 million years just to cross it from one edge to the other. Think of it like trying to find a completely empty parking lot in the middle of Manhattan. Except this parking lot is larger not only than Manhattan, but also the entire state of New York and even the entire continental United States. It's a region of space where matter simply chose not to exist. This discovery sent shockwaves through the astronomical community. How could such a massive region contain almost nothing? Where had all the matter gone? Had it never formed there in the first place? Or had it been somehow pushed out by forces we are yet unable to comprehend? Kirshner named his discovery the Bootes Void after the constellation where he found it. Other scientists began calling it the Great Nothing or the Cold Spot. As increasingly powerful telescopes turned towards this mysterious region, the mystery only deepened. One study after another confirmed the impossible. This was not just a gap between galaxies. It was a genuine hole in the very fabric of the universe. The void challenged everything astronomers knew about large-scale cosmic structure. If the universe formed from tiny density fluctuations after the Big Bang, how could such a massive region remain so utterly empty? What force could be powerful enough to prevent galaxies from forming in such a vast volume of space? As Kirshner continued to map the void's boundaries, he realized he had found something far stranger than anyone could have imagined. The void was not random. It had a structure. It had a purpose. And deep within its heart, a handful of galaxies hung in the impenetrable darkness, like lonely islands in an endless ocean. But these survivor galaxies held secrets that made the mystery even more terrifying. When astronomers first calculated how many galaxies should exist in the Bootes Void, they expected to find about 2,000 bright, star-filled systems scattered throughout the region. However, they found only 8. 8 solitary galaxies floating in a space that, by all calculations, should have contained 2,000. Imagine walking into a concert hall designed for 2,000 people and finding only 8 scattered individuals sitting in complete darkness. The silence in such a hall would be deafening, and the void itself would feel fundamentally wrong. These 8 surviving galactic formations were dubbed void galaxies, and their behavior was entirely inconsistent with established patterns of galactic existence. Ordinary galaxies typically inhabit neighborhoods. They tend to cluster together, gravitationally bound in groups and vast superclusters. There is constant exchange of matter between them, sometimes even collisions and subsequent mergers occurring over billions of years. They exist within a cosmic community where no galaxy is truly alone. However, void galaxies represent a completely different phenomenon. They are cosmic recluses, whose degree of isolation surpasses all previously recorded observations. The nearest galactic neighbor to any of these objects is typically about 50 million light-years away. For context, our own nearest large galactic neighbor, the Andromeda Galaxy, is only 2 million light-years from the Milky Way. Thus, void galaxies are 20 times more isolated than we are. Such a degree of isolation had a profound impact on their evolutionary development. In the absence of nearby galaxies with which to interact, they evolved in conditions of cosmic solitude. Many of them are strikingly small and dim, giving the impression that the surrounding emptiness somehow stunted their growth. They contain fewer heavy elements compared to galaxies of similar age located in standard regions of cosmic space. Their star formation rate is unusually low, leading to the formation of galaxies that appear almost dormant compared to the bustling star factories observed in other regions. Scientists call this phenomenon galactic underdensity. However, this dry scientific term cannot convey the true strangeness of what we see. These galaxies are separated not just by distance, they are separated by such profound emptiness that it affects their very essence. They are like children raised in complete isolation, developing differently than in a normal cosmic environment. The mathematical probability of finding such a significant underdensity by chance is less than 1 in a million. The universe should not be able to create such a vast void through ordinary cosmological processes. The Big Bang undoubtedly left behind tiny fluctuations in density, but these variations should have averaged out on such enormous scales. Finding a region so devoid of matter is like flipping a coin and getting heads 1,000,000 times in a row. Nevertheless, this phenomenon exists, challenging our most fundamental ideas about cosmic evolution. The void galaxies themselves seem to know that something is wrong with their existence. Their peculiar properties indicate that they were formed under the influence of forces we have yet to comprehend. Forces capable of carving out immense chasms in the very fabric of space-time. The mystery deepens when we analyze the precise location of these 8 survivors within their cosmic prison. The 8 galaxies trapped in the Boots void are not randomly scattered across its boundless expanse. They are arranged in a perfect tubular structure. Imagine a massive, invisible underground tunnel stretching for 300 million light-years. Now imagine 8 subway stations evenly spaced along this tunnel. Each one emits the light of billions of stars. This is how the void galaxies are arranged, forming what astronomers call a filamentary structure piercing the heart of the great nothing. Such an arrangement should be impossible. In ordinary regions of cosmic space, galaxies tend to gather around the densest zones, following the gravitational pull of dark matter. They form webs, sheets, and clusters, but always obey the underlying structure of matter distribution. Randomness cannot explain why 8 isolated galaxies would align into such a precise formation. This tube stretches from one edge of the void to the other, like a cosmic highway connecting distant shores of ordinary space. Each galaxy is approximately 40 million light-years from its nearest neighbor along this invisible line. They are like streetlights on an incredibly long and desolate road, marking a path through the boundless darkness. This filamentary arrangement indicates that the void is not just empty space. Something must have guided these galaxies into such a formation. Some deep, invisible structure to our telescopes must exist within this void. Perhaps it is dark matter, or some other form of matter that we have not yet learned to detect. Scientists have hypothesized that this tube represents a kind of fossil of the early universe. During the first few 100 million years after the Big Bang, matter was distributed differently than it is today. Perhaps the void galaxies mark the location of an ancient filament of dark matter that once connected distant regions of space. As the universe expanded and evolved, most of the matter was pulled away from this region, leaving only this ghostly filament. The galaxies themselves, situated within this gigantic structure, exhibit clear signs of unusual behavior, which in turn serves as reliable confirmation of the proposed theory. All of them move in a single direction, as if obeying an invisible cosmic current. Their velocities are perfectly synchronized, suggesting they are responding to the same powerful gravitational influence. However, we are still unable to detect the source of this attraction. Spectroscopic analysis convincingly shows that galaxies located in the void contain significantly fewer heavy elements compared to galaxies of similar age residing in ordinary, denser regions of the universe. This fact suggests that they formed in an environment with significantly less dense matter, which fully supports the hypothesis that this region has been underdense since the universe was only 380,000 years old. These galaxies are essentially cosmic time capsules, carefully preserving conditions characteristic of an earlier era of cosmic evolution. The proposed tubular structure also perfectly explains why the void appears so incredibly empty from most angles. If viewed from the side, we would see the void edge on, and it would appear as a thin, barely perceptible line of galaxies against the boundless emptiness. However, from most other angles, the galaxies are arranged in such a way that they appear as merely a single point of light. This astonishing cosmic optical illusion makes the void appear even emptier than it actually is. But the true terrifying scale of the void only becomes apparent when we begin to measure the rate at which this cosmic emptiness is steadily growing. The Boötes void is not a static region of space. It is actively expanding and significantly faster than the universe itself, becoming more and more empty with each passing million years. Imagine a balloon with a small hole on its surface that continues to grow. As you inflate the balloon, the hole doesn't just maintain its original size. It expands proportionally, consuming more and more of the balloon's surface. The Boötes void behaves in precisely the same way. But instead of consuming rubber, it consumes the very space where galaxies should exist. Measurements convincingly show that the void is expanding approximately 10% faster than the cosmic expansion caused by mysterious dark energy. This may seem like an insignificant difference, but on grand cosmic timescales, it represents a fundamental deviation from how space should behave according to accepted models. While ordinary regions of the universe expand under the influence of dark energy, the void appears to be actively repelling matter, steadily pushing galaxies away from its boundaries. This accelerated expansion gives rise to a phenomenon that scientists call void instability. Once an area becomes underdense, it becomes much easier for matter to flow out of it than to flow in. Gravity, which normally attracts matter, acts in the completely opposite direction on these scales. Instead of attracting nearby galaxies, the emptiness of the void creates a gravitational gradient that literally pushes matter towards denser regions. Think of it like water flowing downhill. Normally, galaxies are attracted to areas of high matter density, just as water flows to the bottom of a valley. But in the void, the emptiness itself creates a kind of uphill slope. Matter naturally flows away from the void, towards regions where other galaxies already exist. This forms a feedback loop, where emptiness creates even more emptiness, amplifying this process. Mathematical models developed to describe this phenomenon look quite unsettling. If current expansion rates persist, the Boötes void will double in size within the next 5 billion years. By the time our sun completely burns out, this region of space will be twice as empty as it is today. The 8 survivor galaxies will be pushed even further apart, and their isolation will become even deeper and more pervasive. But the rate of expansion suggests something even more unsettling and mysterious. The void is not just growing due to ordinary cosmic expansion. Something is actively pushing matter away from this region. Dark energy, which is responsible for the accelerated expansion of the entire universe, seems to be more strongly concentrated within the void. This creates a kind of cosmic vacuum cleaner that effectively sucks matter density out of this region, making it increasingly empty. Some theoretical physicists hypothesize that we are witnessing the birth of a cosmic false vacuum bubble. In this scenario, the very laws of physics might be significantly different inside the void. The vacuum state of space could be unstable, leading to its exponential expansion and the expulsion of all matter to its boundaries. If this theory is correct, then the void represents a kind of glimpse into what the entire universe might look like in the distant future when it reaches a similar state. The expansion of cosmic space also significantly impacts how we perceive the void from our planet. Light rays originating from the few galaxies located in this vast region exhibit a significantly greater redshift than would be expected. They are stretched to longer wavelengths due to the extraordinarily high expansion rate. This phenomenon causes void galaxies to appear more distant and dimmer to us than they actually are. As this cosmic emptiness grows in size, it actively begins to affect the surrounding cosmic neighborhoods. Along the borders of the Boots void, galaxies cluster together, forming unusually dense walls as if trying to escape something terrible located within the void. These boundary zones contain approximately 3 times more galaxies compared to ordinary regions of cosmic space. Imagine a large crowd of people pressed against the walls of a room, each trying to stay as far away as possible from something frightening in the center. The galaxies surrounding the void behave in precisely this way, gathering into dense filaments and sheets that form a kind of cosmic containment barrier. Scientists have named these structures void walls, and they represent one of the most extreme examples of large-scale structure in the known universe. These walls stretch for hundreds of millions of light-years, forming massive curtains of galaxies that separate the void from ordinary space. Some individual segments of these walls contain over 10,000 galaxies packed into areas that would normally hold only 3,000. The density gradient is so striking that you can literally see where ordinary cosmic space ends and the void begins. This can be compared to standing at the edge of the ocean and observing where the water meets a deserted beach. The transition occurs in a relatively narrow zone, perhaps about 20 million light-years wide. On one side, galaxies cluster in familiar cosmic abundance. On the other side, almost nothing. This sharp boundary violates our established understanding of how matter should be distributed in the universe. Density variations in cosmic space should be smooth and gradual, following the gentle curves of gravitational influence. However, instead, the void creates a sharp, abrupt drop in galaxy density, suggesting that some violent process carved this giant hole in space. The void walls themselves show signs of unusual behavior. Galaxies within these walls move faster than expected, as if some force is actively pushing them away from the interior of the void. Their peculiar motions suggest that a repulsive force is acting within the void, creating what physicists call a negative pressure gradient. Computer simulations have significant difficulty reproducing these wall structures through ordinary gravitational processes. Even when scientists start simulations with the most extreme possible initial conditions, they still cannot create void walls as dense as those observed around Boötes. It seems that some additional force or exotic form of matter is required to explain the existence of these walls. The walls also influence how light propagates through this region of cosmic space. Photons from distant galaxies are deflected as they pass through the dense regions of the walls, creating subtle gravitational lensing effects. This causes galaxies located behind the void to appear slightly distorted, as if we are observing them through cosmic funhouse mirrors. Most unsettling is what happens to galaxies that get too close to the void's boundary. Astronomical surveys have revealed several groups of galaxies that appear to be in the process of being absorbed by the void. These falling galaxies exhibit elongated shapes and unusual star formation patterns, as if they are being stretched and torn apart by tidal forces associated with the void. The walls represent a cosmic battle between emptiness and matter, where galaxies desperately cluster together to resist absorption by the growing hole in space. But to understand how such walls could have formed, we must examine the mysterious physics that allows matter to avoid certain regions of space for billions of years. The Booty's void exists because matter has been leaving this region of cosmic space for over 13 billion years. And the physics behind this cosmic refusal reveals forces we are only just beginning to understand. In the early universe, tiny quantum fluctuations created regions that were either slightly denser or slightly less dense than average. These fluctuations were incredibly small, representing differences of only 1 part in 100,000. Over time, gravity should have smoothed out these variations, pulling matter from less dense regions into denser ones. But something went wrong in the region that would become the Booty's void. Instead of smoothing out, the underdensity became even more extreme. Matter did not simply avoid this region, it actively fled from it, creating an emptiness that defies gravitational logic. Consider gravity as a vast landscape, abundant with hills and valleys. In familiar regions of cosmic space, gentle slopes prevail, along which any matter, as if on an inclined plane, tends towards areas of increased density. However, the region known as the void appears to possess an upward slope that actively repels matter. This phenomenon gives rise to what physicists define as a repulsive gravitational field. While the mechanism of this repulsion still remains one of the universe's greatest mysteries, there is a hypothesis linking it to dark energy, the very same mysterious force responsible for the accelerated expansion of the entire cosmos. Normally, dark energy is uniformly distributed throughout cosmic space. But according to theoretical models, under certain unique conditions, it can concentrate in specific regions. If we assume that dark energy has a higher density within the void, this would lead to a repulsive force strong enough to effectively displace ordinary matter. Another explanation for this phenomenon is linked to exotic states of matter that may have existed in the early periods of the universe. In the first moments after the Big Bang, space itself might have undergone phase transitions, analogous to the process of water turning into ice. Some regions could have gotten stuck in a different phase, thereby forming pockets of space with altered physical properties. There is also a suggestion that the void represents a region where dark matter never properly condensed in the early universe. Dark matter plays a key role in forming the gravitational scaffolding upon which ordinary matter subsequently builds galaxies and larger cosmic structures. In the absence of such scaffolding, ordinary matter would lack the foundation for coalescing into clusters. As a result, such a region would forever remain desolate, unable to form the dense concentrations necessary for the emergence of galaxies. Measurements of the cosmic microwave background, CMB, the ancient light left over from the Big Bang, confirm this theory. They show a cold spot in the direction of the Booty's void, indicating that this region has been underdense since the universe was only 380,000 years old. This cold spot is a kind of fossil evidence, pointing to the void's ancient origins. Computer simulations demonstrate that creating such an extreme underdensity requires initial conditions that are statistically almost impossible. The probability that random fluctuations could produce such a vast void is less than 1 in 10 million. This suggests that the void may not be a result of chance, but rather a consequence of some systematic process that was actively at play in the universe's infancy. Some theoretical physicists propose that cosmic inflation, a period of exponential expansion in the early universe, might have operated differently in this region. Inflation usually smooths out irregularities, but under certain conditions it could have, on the contrary, amplified them, leading to the formation of regions of extreme emptiness or, conversely, extreme density. The physics becomes even more enigmatic when we begin to investigate how this void affects the very fabric of space-time. The Booty's void doesn't just contain empty space, it actually alters the properties of space and time within its boundaries, giving rise to a region where the laws of physics we are accustomed to operate differently. Albert Einstein's general theory of relativity states that matter and energy warp spacetime, creating what we perceive as gravity. Massive objects like stars and planets form depressions in spacetime, while less massive regions create gentler curvatures. But what happens in a region where there is virtually no matter? The void gives rise to what physicists call negative spacetime curvature. Instead of matter curving space inward, the absence of matter allows space to curve outward, creating a cosmic shape resembling a saddle. This unusual geometry affects how light propagates through this region and how time itself flows within the void. Light rays passing through the void follow trajectories that subtly differ from what we would expect in ordinary space. Instead of traveling in perfectly straight lines, photons are slightly curved outward, following the unusual geometry of the underdense region, causing light from distant galaxies to spread wider than it should. The effect of such a cosmic structure, though measurable, is quite subtle. When astronomers point their telescopes at galaxies located beyond the void, these celestial objects appear somewhat dimmer and blurrier than predicted. The void thus functions like a cosmic lens, but with an inverse action, diminishing and dimming objects in the background. This phenomenon of gravitational lensing serves as direct and irrefutable proof that the void itself, despite its rarefaction, exerts tangible gravitational effects on the surrounding space. The flow of time within the void also exhibits its unique characteristics, differing from the pace in denser regions of cosmic space. According to the postulates of Albert Einstein's general theory of relativity, time moves faster in regions where gravitational fields are weaker. Since the void contains significantly less matter compared to ordinary galaxy clusters, hypothetical clocks placed inside the void would tick slightly faster than their counterparts located in galaxy-rich regions. This effect of time dilation, or more precisely, its acceleration within the void, is extremely small, amounting to only a few parts per billion. But it points to a fundamental difference in the mechanisms of spacetime itself. The void also influences the propagation of gravitational waves. These subtle ripples in the fabric of spacetime, whose existence was experimentally confirmed in 2015, typically travel at the speed of light through ordinary cosmic space. However, when passing through the void, gravitational waves undergo slight but measurable changes in their amplitude and frequency. These changes are due to the unusual geometry of spacetime, characteristic of rarefied regions. In the future, gravitational wave detectors may be able to use these effects to construct three-dimensional maps of the structure of cosmic voids. A region of reduced matter density gives rise to a phenomenon that cosmologists call the gravitational Doppler effect. When light emerges from a shallow gravitational well formed by the boundaries of the void, it loses some of its energy and shifts towards the red end of the spectrum. This effect is fundamentally different from cosmological redshift, which is caused by the universal expansion of the universe, and adds an additional layer of complexity to the process of measuring cosmic distances. Some theoretical physicists hypothesize that the void may harbor exotic forms of matter that are currently beyond direct detection. These hypothetical particles could possess negative energy density, creating repulsive gravitational effects. These effects, according to scientists, could explain the unusual properties of the void. Such exotic matter remains only a theoretical supposition for now, but its existence would radically change our understanding of what types of materials can form the universe. The geometry of spacetime within the void also affects the trajectories of cosmic rays passing through this region. High-energy particles arriving from distant sources follow curved paths through the anomalous gravitational field of the void. This leads to the formation of so-called shadow zones, where cosmic rays deviate from their usual trajectories. These gravitational effects extend far beyond the visible boundaries of the void, influencing the cosmic microwave background over vast regions of the celestial sphere. The Boots void casts a distinct cold shadow on the cosmic microwave background, CMB, the ancient light of the Big Bang. This phenomenon clearly demonstrates how this void influenced the universe from its earliest stages. The CMB is the oldest light in the universe, released when the cosmos was only 380,000 years old. In theory, this radiation should be almost perfectly uniform across the sky, showing only microscopic temperature variations that reflect the density fluctuations present in the early universe. However, in the direction of the Boots void, an anomalously cold spot is observed that should not be there. This cold spot spans several degrees on the celestial sphere, making it one of the largest and most coherent features in the CMB. The temperature difference is only about 30 millionths of a degree. However, this tiny change represents a profound anomaly in the baby picture of the universe. It suggests that the region where the void now resides was significantly less dense even when the universe was less than 1% of its current age. The cold spot forms as a result of a process known as the integrated Sachs-Wolf effect. When CMB photons pass through regions with varying gravitational potential, they either gain or lose energy. In the case where light passes through a region that becomes less dense over time, it loses energy and consequently becomes colder. The Bootes void has been emptying out for billions of years, creating precisely this effect. Imagine it as a kind of cosmic tax on light. As photons escape the void's evolving gravitational field, they pay an energy toll that makes them slightly redder and colder than they were upon entering the region. This process has been active for over 13 billion years, gradually carving a cold imprint into the universe's background radiation. The magnitude and intensity of the cold spot provide crucial information about the void's history. Using computer models, it's possible to work backward from the observed temperature decrement to determine exactly how the void evolved over time. These calculations suggest that the void was initially a relatively moderate underdensity in the early universe and has since become increasingly empty. However, the cold spot reveals an additional mystery. According to standard cosmological models, the temperature decrement should be even larger than what is observed. The measured cold spot is approximately half as intense as theoretical predictions suggest. This discrepancy hints that our existing understanding of how voids evolve may be incomplete, or that exotic physics is at play within these empty regions. Some cosmologists propose that the cold spot's imprint was partially erased by secondary effects. As CMB photons pass through the void, they may interact with hot gas or energetic processes that return heat to the radiation. This could explain why the cold spot appears weaker than expected. The angular size of the cold spot also provides information about the void's three-dimensional structure. By measuring how the temperature decrement varies in different directions, astronomers can map the void's shape and orientation relative to our line of sight. These measurements confirm that the void is observed almost face-on, spanning its full 300 million light-year size. Other cosmic voids create their own cold spots in the microwave background, but none compare in size or distinctness to the Bootes imprint. This supports the idea that the Bootes void represents an extreme example of cosmic underdensity, significantly exceeding what ordinary statistical fluctuations should produce. The cold spot also affects how fundamental cosmological parameters are measured. The temperature pattern provides independent evidence for the existence of dark energy and helps constrain models of cosmic inflation. This ancient imprint raises troubling questions about whether the void represents one giant hole in space or something even stranger. Recent deep surveys suggest that the Bootes void may not be a single empty region, but rather 3 or 4 smaller voids that have merged to form one massive hole in space. High-resolution galaxy surveys using the Sloan Digital Sky Survey and other large telescopes have mapped the internal structure of the void with unprecedented detail. Instead of finding a homogeneous emptiness, astronomers have found evidence of multiple overlapping underdense regions, each with its own distinctive properties and evolutionary history. Imagine 3 soap bubbles floating in water that gradually approach and merge into one large bubble. The Bootes void appears to have formed from a similar process, where smaller voids coalesced over billions of years to create the enormous emptiness observed today. Each constituent void contributes its characteristics to the final merged structure. Evidence for multiple voids comes from the peculiar distribution of the few galaxies found in the region. Instead of being randomly scattered throughout the void, these galaxies are clustered in small groups that appear to mark the boundaries between the original constituent voids. The 8 bright galaxies form a tubular structure that may represent a boundary where 2 large voids merged. Computer simulations support this merger scenario. Models that start with several smaller, underdense regions in the early universe can reproduce the observed structure of the Boots void more accurately than simulations assuming a single large empty region. The merger process naturally explains the elongated shape of the void and the peculiar arrangement of galaxies within it. It appears that each of the constituent voids formed at slightly different times in cosmic history. Spectroscopic investigations conducted on the few galaxies located in this space reveal subtle differences in their stellar populations and chemical composition. These discrepancies suggest that different parts of the void remained empty for varying periods, confirming the merger hypothesis. The northern region of the void contains galaxies that are slightly older and poorer in metals than those located in its southern part. This gradient indicates that the northern void formed earlier and remained empty longer, which in turn provided less time for star formation and chemical enrichment processes in the galaxies that managed to survive there. The merger process also explains the unusually high expansion rate of the void. When smaller voids merge, their gravitational effects combine, forming a larger region with enhanced repulsive characteristics. The combined void expands at a faster rate than any of its constituent parts individually, accelerating the process of cosmic evacuation. Theoretical models predict that void mergers should be a relatively common phenomenon in the later stages of the universe's development. As cosmic expansion continues and dark energy's dominance strengthens, smaller voids should naturally grow in size and merge into larger empty spaces. The Bootes void may be a kind of harbinger of what much of the universe will look like in the distant future. The merger scenario also helps explain why the void significantly exceeds the predictions of statistical models based on random density fluctuations. While the probability of a single void of such mass forming is incredibly low, the probability of several smaller voids appearing and subsequently merging is significantly higher. The observed structure may be the result of a series of unlikely but not impossible events. Deep radio surveys have found additional evidence supporting the merger hypothesis. The few galaxies located in the void exhibit unusual radio emission patterns, suggesting they have been affected by multiple episodes of environmental change. These galaxies bear the marks of having experienced several void merger events over billions of years. However, regardless of whether the void formed as one colossal whole or as the result of the merger of several monsters, its existence points to the action of forces whose scales extend beyond ordinary cosmic evolution. The Bootes void can serve as a natural laboratory where dark energy acts more powerfully than anywhere else in the universe, revealing clues to understanding the mysterious force driving cosmic acceleration. Dark energy accounts for 68% of the universe, yet humanity knows almost nothing about its nature or properties. It is known to cause space itself to expand at an accelerating rate, but scientists cannot detect it directly or explain why it exists. The Bootes void provides a unique opportunity to study dark energy in isolation, away from the complicating effects of matter and radiation. In ordinary regions of space, the effects of dark energy are subtle and difficult to measure. The presence of galaxies, dark matter, and other forms of energy creates a complex gravitational environment where the influence of dark energy is masked by stronger forces. But inside the void, these masking effects are almost entirely absent. The void creates a pristine environment where the properties of dark energy become more apparent. Measurements show that space within the void expands faster than the cosmic average. This accelerated expansion suggests that dark energy may be more concentrated or more active in under-dense regions. One can imagine dark energy as a gas that becomes more powerful when it has more room to act. In the compressed environment around galaxies, the effects of dark energy are suppressed. In the vast emptiness of the void, it can exert its full influence. Some theoretical models suggest that dark energy is not actually constant throughout space and time. These quintessence models assert that the strength of dark energy varies depending on local conditions, becoming stronger in regions of lower matter density. The Bootes void provides an ideal testing ground for these theories, offering an environment where matter density is essentially zero. The rate at which the void expands also provides valuable insights into the equation of state of dark energy, a fundamental property that defines the nature of its influence in various cosmic conditions. By analyzing the void's growth rate over time and comparing it with theoretical models, cosmologists can narrow down the possible explanations for the nature of dark energy, ruling out some of the more exotic and improbable hypotheses. Observations of the cosmic microwave background temperature originating from the direction of the void confirm the hypothesis that dark energy manifests differently there than in denser regions of the universe. The recorded cold spot perfectly aligns with the concept of enhanced dark energy activity, which has actively pushed matter out of this region for billions of years. This creates a kind of feedback loop where the void, becoming increasingly vast, amplifies the effects of dark energy, which in turn leads to the formation of even greater emptiness. The void may also help resolve one of the greatest and most intriguing puzzles in modern cosmology, the so-called cosmic coincidence problem. The question arises, why does the density of dark energy seem to have been perfectly tuned to become dominant precisely in the current epoch of cosmic evolution? The void's properties hint that the influence of dark energy depends on the density of surrounding matter, potentially offering a natural and elegant explanation for this apparent fine-tuning, eliminating the need to resort to the anthropic principle. Future generations of space telescopes will use the void as a kind of natural laboratory to study dark energy. By tracking the evolution of the void's boundaries over time and measuring the peculiar velocities of galaxies located near its edges, scientists will be able to create a detailed map of dark energy's influence with unprecedented accuracy. These observations could definitively clarify whether dark energy is truly an immutable constant, or if its properties vary in space and time. Furthermore, the void offers a unique opportunity to understand the connection between dark energy and cosmic inflation, a period of exponential expansion that occurred in the very early universe. Some theoretical models suggest that dark energy is a residual field of the inflaton, which was the driving force behind cosmic inflation. If this assumption is correct, the void may preserve imprints of that ancient era, offering us a unique window into the very first moments of the universe's existence. However, the void's connection to dark energy inevitably raises a number of troubling questions about the ultimate fate of the universe and what this grand emptiness tells us about the cosmos we inhabit. This extraordinary void clearly demonstrates that our universe contains regions where the laws we are accustomed to seem to break down, where forces we are only just beginning to understand shape reality on scales far exceeding human comprehension. As we delve deeper into the mysteries of the Bootes void, we discover that the cosmos is far stranger and more enigmatic than we ever could have imagined. At the boundaries of the Bootes void, gravity itself behaves non-trivially, creating a kind of cosmic desert where matter literally flows outward, like water rushing from a burst dam. Ordinary gravity attracts matter, forming the intricate cosmic web of galaxies and dark matter filaments that we observe throughout most of the universe. However, at the edges of the void, the gravitational influence manifests in the opposite direction. Instead of attracting matter, the cumulative gravitational effect of the surrounding emptiness creates a repulsive force that actively pushes galaxies out of the void's interior. This inversion of gravitational behavior is explained by what physicists call the inverse Birkhoff's theorem. In regions of extreme underdensity, meaning with virtually no matter, a negative gravitational potential forms, which functionally acts as an anti-gravitational field. Galaxies located near the void's boundaries experience a force that pulls them towards regions of higher matter density, effectively sucking material out of the empty region. Measurements of galaxy velocities near the void confirm this unusual gravitational behavior. Galaxies located within 50 million light-years of the void's edge are receding from the empty region at speeds reaching 600 meters per second, significantly faster than would be expected from cosmic expansion alone. These peculiar velocities unequivocally indicate that some force is actively repelling matter from the void. Notably, this effect intensifies closer to the void's center. Computer simulations demonstrate that any galaxy unlucky enough to accidentally find itself within the void's interior would be accelerated outward by these gravitational forces, unable to maintain a stable orbit in this empty region. Thus, the void acts as a kind of cosmic vacuum cleaner in reverse, actively pushing out any matter that dares to venture into its domain. Such unusual gravitational behavior undoubtedly explains why the few galaxies that did manage to survive within the void possess such peculiar characteristics. They are like cosmic survivors who have passed through a grand evacuation process that has relentlessly operated for billions of years. These stellar systems managed to form in the dawn of the universe, before the repulsive effects of the void became dominant, but since then, they have been steadily deprived of the new building material necessary for their growth and development. The repulsive gravitational field, it turns out, also affects the dynamics of dark matter in this vast region. Although we are not yet able to directly observe dark matter, advanced computer simulations convincingly demonstrate that particles of this mysterious substance must also be pushed out of the void by the same gravitational forces that affect ordinary matter. This leads to the emergence of a region where even the invisible scaffolding supporting cosmic structure has been destroyed and deformed. The gravitational desert of the void extends far beyond its visible boundaries. Careful astronomical surveys convincingly show that the rate of new galaxy formation is significantly suppressed in a zone that extends for 100 million light-years beyond the very edge of the void. This vast gravitational shadow profoundly influences how matter accumulates in a colossal region of cosmic space, creating underdensities that cascade outward from the central void, like ripples on water. Temperature measurements provide additional, very convincing evidence of these unusual gravitational effects. Gas rushing towards the void's boundaries should logically heat up as it accelerates under gravitational influence. However, observations record the opposite. The intergalactic gas near the void is actually colder than expected, suggesting that the gravitational field performs negative work on this material, cooling it rather than heating it, contrary to conventional wisdom. Repulsive gravity also influences how cosmic rays propagate through this unique region of space. High-energy particles arriving from distant sources are deflected away from the void, creating a kind of cosmic ray shadow that extends for several degrees across the celestial sphere. This unique effect serves as yet another independent confirmation that the void's gravitational field operates quite differently than in ordinary space, where matter is more uniformly distributed. Some prominent theoretical physicists even hypothesize that the unusual gravity of the void could serve as direct evidence for modified theories of gravity. While Albert Einstein's general theory of relativity performs admirably in regions of normal matter density, it may require certain modifications in extreme environments, such as cosmic voids. The Bootes void, in this context, could act as a unique testing ground for these alternative theories, opening new horizons in our understanding of gravity. The gravitational desert creates conditions that challenge our established understanding of how cosmic structure should evolve, raising fundamental questions about the cosmic web itself. The Bootes void represents a catastrophic failure in the cosmic web, the largest structure in the universe, convincingly revealing that our current models of matter organization on cosmic scales are fundamentally incomplete and require refinement. The cosmic web is the grand framework upon which all cosmic structure is built. Dark matter forms invisible filaments connecting giant galaxy clusters, creating an intricate three-dimensional network that spans the entire observable universe. Galaxies, in turn, form where these filaments intersect, while vast empty regions, called voids, exist in the spaces between these filaments. This web-like structure, by all accounts, should be continuous and connected throughout space. However, the Boötes void violates this fundamental rule, representing a massive hole in the cosmic web where the filaments connecting distant regions of space are absent. Imagine a spiderweb from which a huge section has been completely torn out, leaving only loose threads dangling helplessly in the empty air. The Boötes void creates precisely such a topological defect in the universe's largest structure, challenging our models. Advanced computer simulations of cosmic structure formation, even with the most sophisticated algorithms, cannot reproduce voids as massive and empty as the Boötes void using standard models of dark matter and gravity. Even when scientists start these simulations with the most extreme possible initial conditions, they are still unable to create such massive holes in the cosmic web. The very existence of the Boötes void strongly suggests that our understanding of how structure forms in the universe is missing key components, requiring further investigation and rethinking. The disruption in the cosmic web, which is the foundation of all large-scale structure in the universe, generates cascading effects that spread across vast surrounding regions. Filaments that would normally connect to the far side of the void are here severed, abruptly terminating at its boundaries. This circumstance leads to the formation of so-called orphan galaxy clusters, deprived of their usual cosmic context. They appear as isolated islands of matter, surrounded by anomalous emptiness. Notably, the rate of new galaxy formation is significantly suppressed throughout the vast regions surrounding the void, indicating that the network disruption propagates far beyond the empty region itself. New galactic structures cannot form without the gravitational scaffolding provided by dark matter filaments. Thus, the absence of this network creates a vast zone of cosmic barrenness, spanning hundreds of millions of light-years. The void also significantly disrupts the normal flow of matter through the cosmic web. In healthy, anomaly-free regions of the web, matter flows along filaments, heading towards intersection points where galaxy clusters form. However, the void creates a kind of cosmic funnel that interrupts these flows, causing matter to accumulate at the void's boundaries instead of following its usual trajectory through the intricate structure of the cosmic web. Measurements of the cosmic microwave background, the universe's oldest light, show that this network disruption dates back to the earliest epochs of cosmic development. The temperature patterns recorded in this ancient radiation indicate that this region initially lacked the normal network of density fluctuations that should have provided the seeds for the subsequent formation of the cosmic web. In other words, the cosmic web was torn here from its very inception. Some cosmologists hypothesize that the void represents the boundary of a cosmic region where different regions of spacetime meet, possessing incompatible properties. During cosmic inflation, which occurred in the early universe, different regions might have had slightly different expansion histories, leading to the creation of boundaries where the cosmic web could not properly connect. The network disruption also affects how information propagates throughout the universe. In ordinary regions, gravitational influences spread along the network's filaments, allowing distant parts of the universe to remain causally connected. However, the void creates a kind of communication gap where gravitational information cannot flow freely, thereby isolating regions on either side of this void. Advanced statistical analysis demonstrates that the void's influence on the cosmic web extends to scales ranging from individual galaxies to giant superclusters. The topology of the web is fundamentally altered across an entire region spanning almost 1 billion light-years of space, making this the largest known structural defect in the universe. The torn web gives rise to what cosmologists call frustrated cosmic evolution, where normal structure formation processes are effectively prevented from functioning. This structural disruption has profound implications for how dark matter, the invisible foundation of cosmic structure, is distributed across this vast region of space. The Booty's void poses a serious challenge to everything known about the distribution of dark matter, suggesting that the invisible foundation of cosmic structure may be arranged in a way that violates the most basic theoretical assumptions. Dark matter accounts for 85% of all matter in the universe, yet it interacts only through gravity, making it invisible to direct observation. Scientists infer its presence from its gravitational effects on ordinary matter and from computer simulations that require the presence of dark matter to explain how galaxies and larger structures form. According to these models, dark matter should be distributed relatively uniformly throughout space, with concentrations marking the locations where galaxies will eventually form. However, the Booty's void appears to contain almost no dark matter at all. Gravitational lensing measurements, which reveal the presence of dark matter by its bending of light from background galaxies, show that the dark matter density in the void region is less than 10% of the cosmic average. This represents one of the most extreme dark matter deficits ever discovered in the universe. The absence of dark matter creates a profound mystery. In standard cosmological models, dark matter provides the gravitational scaffolding that allows ordinary matter to clump together and form galaxies. Without this invisible framework, galaxy formation should be impossible. Yet the void contains 8 survivor galaxies that somehow manage to form despite the lack of dark matter support. Computer models face significant difficulties in explaining how such a pronounced underdensity of dark matter could arise from ordinary gravitational interactions. Even in the most rarefied regions predicted by current theoretical constructs, dark matter, according to calculations, should retain at least 30% of the average cosmic density. However, the dark matter content of the Booty's void significantly falls short of this minimum threshold, calling into question the adequacy of existing models. Some physicists hypothesize that the void may contain a different type of dark matter with unusual characteristics. Instead of the familiar cold dark matter, which moves slowly and clumps together under gravity, the void is likely filled with warm or even hot dark matter. These particles move at such high speeds that they are unable to form stable concentrations. Such an exotic form of dark matter would remain effectively invisible to all current detection methods. Another possible interpretation is related to self-interacting dark matter. Most current dark matter models assume that its particles interact with each other only through gravity. However, some theories allow for dark matter to interact with itself through as yet unknown forces. In regions where the dark matter density becomes extremely low, these self-interactions could lead to the annihilation or decay of the remaining dark matter particles. This creates a self-sustaining feedback loop that completely empties the region, making it virtually devoid of dark matter. The dark matter deficit in the Booty's void also impacts how we interpret gravitational lensing observations throughout the surrounding region. Light from distant galaxies passing near the void should be deflected less than expected due to the significantly reduced gravitational influence. Such a phenomenon introduces systematic errors in distance measurements and mass estimates for background cosmic objects. Measurements of the rotation curves of galaxies located within the void provide additional clues to understanding dark matter behavior. The few galaxies existing in this unusual region exhibit anomalous rotation patterns. These patterns indicate that they contain less dark matter than similar galaxies in more typical cosmic environments. This observation reinforces the idea that dark matter has been actively removed from this entire vast region. Some cosmologists suggest that the void may serve as evidence for alternative theories of gravity that do not require the existence of dark matter at all. Modified theories of gravity, such as MOND, or modified Newtonian dynamics, predict that gravitational effects should manifest differently in extremely low-density environments. Thus, the void could act as a natural laboratory for testing these alternative theoretical concepts. The mystery of dark matter deepens further when considering that the few void galaxies show signs of having formed through normal processes, despite their dark matter-poor environment. Their stellar populations and chemical compositions are consistent with standard galaxy formation models, yet they exist in a region where such formation should, by all accounts, be impossible. Advanced computer simulations using various dark matter models cannot reproduce the extreme properties of the void, suggesting that our understanding of dark matter behavior in underdense environments is fundamentally flawed. This dark matter enigma raises questions about how ordinary matter moves through regions of extreme cosmic underdensity. Matter flows around the Bootes void like cosmic rivers circumventing a giant stone, creating flow patterns that reveal the invisible forces shaping large-scale structure throughout the universe. Galaxy surveys demonstrate that matter does not simply randomly avoid the void. Instead, galaxies and dark matter form coherent streams that flow around the empty region along predictable trajectories. These grand cosmic currents follow paths determined by the void's gravitational influence, creating a hydrodynamic flow pattern on scales of hundreds of millions of light-years. The most impressive of these flows is the Perseus-Pisces supercluster chain, a massive river of galaxies that curves around the northern boundary of the void. This supercluster chain contains thousands of galaxies flowing in the same direction, all seemingly deflected by their gravitational interaction with the empty region. The flow maintains its coherence over distances spanning almost 500 million light-years. Computer simulations vividly demonstrate that these colossal flows of matter are remarkably stable formations. Once formed, they can persist for billions of years, tirelessly guiding galaxies away from the giant void towards regions with higher concentrations of matter. Thus, these flows function as a kind of cosmic highway, providing preferred routes for matter to travel throughout this vast part of the universe. The intricate flow patterns also shed light on why certain directions around the void contain significantly more galaxies than others. Matter has a pronounced tendency to cluster where several flows converge, thus forming the dense walls of the void that can be observed in specific. These so-called peculiar velocities can exceed 1,000 meters per second, which is a clear indication that powerful gravitational forces are actively driving the formation and development of these flow patterns. Such velocities are among the largest coherent motions ever recorded in the universe. The streaming motion also significantly impacts how galaxies evolve when caught in these flows. Galaxies caught in cosmic currents experience ram pressure as they move through intergalactic gas, leading to the stripping of their outer matter and changes in star formation rates. Many galaxies in these flows show clear signs of recent tidal interactions, suggesting that the fluid environment promotes more frequent galactic collisions. Temperature maps of the cosmic microwave background provide additional compelling evidence for the existence of these grand flows of matter. The oldest radiations show subtle Doppler shifts in directions that precisely correspond to the main locations of the flows, indicating that these flow patterns have been actively at play since the earliest stages of the universe's existence. Thus, these flows are among the oldest and largest-scale structures in the cosmos. The gravitational influence of the void extends far beyond its visible boundaries, affecting the flows of matter in a region spanning over 1 billion light-years. This gravitational basin literally diverts matter from a huge volume of space, contributing to the formation of underdensities that spread far beyond the main empty region. Some of the flows show clear signs of repeated deflection, which is a result of their interaction with the void's evolving gravitational field. As the void grew in size over time, it gradually altered the trajectories of nearby matter flows, creating characteristic curved paths that essentially record the history of this vast region's gravitational evolution. The flow patterns also provide invaluable insights into the three-dimensional structure of dark matter in this region. Although dark matter cannot be directly observed, its gravitational effects on galactic flows clearly demonstrate exactly where invisible concentrations of this mysterious matter exist. These measurements show that dark matter flows follow the same general patterns as ordinary matter, but with subtle differences that reflect the unique properties of dark matter. Advanced statistical analysis convincingly shows that the void's matter flows are closely linked to similar flow patterns observed throughout the observable universe. The Bootes region appears to be an integral part of a global network of cosmic currents that transport matter between various large-scale structures. These flowing rivers of galaxies hold the keys to understanding what the universe might look like in the distant future. The Bootes void offers a truly terrifying glimpse into what the entire universe might look like trillions of years from now, when dark energy stretches space so much that every galaxy becomes an isolated island in a boundless ocean of emptiness. Current cosmological models predict that the expansion of the universe will continue to accelerate indefinitely under the influence of dark energy. Within the next 100 billion years, galaxies beyond our local group will be carried away by cosmic expansion until they disappear beyond our observable horizon. The night sky will gradually become darker as distant galaxies one by one vanish from sight, leaving only a few gravitationally bound systems in our immediate cosmic neighborhood. However, the Bootes void, stretching for many millions of light years, shows us what awaits the universe after such a lonely future. In the deepest isolation characteristic of this void, we observe what happens when cosmic expansion reaches its final conclusion. The few galaxies that manage to survive in the void are separated by such colossal distances that inhabitants of one galaxy would be completely unaware of the existence of any others. Each of these galaxies transforms into a kind of cosmic hermit, immersed in seemingly boundless and silent darkness. The galaxies within the void show clear signs of premature aging, which may foreshadow the fate of all galaxies in the distant future. Cut off from external sources of new material, they consume their gas reserves at an unusually low rate. The process of star formation in them has almost completely stopped, and their stellar populations are dominated by old red stars. These galaxies can rightly be called cosmic retirees, systems that have already exhausted their ability to create new generations of stars. Computer simulations, based on extrapolating current cosmic expansion rates, predict that the entire observable universe will resemble the Bootes void in approximately 10 trillion years. By that time, cosmic expansion will have stretched space so much that galaxy densities throughout the universe will match the extremely low values currently observed exclusively within the void. Every galaxy will experience the same profound isolation that currently affects only the inhabitants of the void. The void also clearly demonstrates how cosmic expansion affects the evolution of life and intelligence. Any civilization developing within the void would face unique and very serious challenges in understanding its cosmic environment. Their night sky would appear almost completely empty, providing no convincing evidence of the existence of other galaxies, or even the phenomenon of cosmic expansion itself. Under such circumstances, they might well come to the erroneous conclusion that their galaxy is the entire universe. This cosmic solitude has profound implications for the development of science and philosophy in isolated galaxies. The cosmic microwave background would still be detectable. However, without other galaxies for comparative analysis, void civilizations might have significant difficulty correctly interpreting its meaning. They would simply lack the necessary observational context, which is crucial for discovering fundamental cosmological principles. The void's expansion rate suggests that this isolation will only intensify over time. Even the 8 survivor galaxies are gradually drifting apart under the accelerating expansion of space within this vast, empty region. Eventually, each void galaxy will lose sight of all others, remaining truly alone in the cosmic darkness. Temperature measurements show that the space within the void is already approaching the ultimate cosmic cold. Due to the very small amount of matter capable of providing heating through gravitational interactions, the void represents one of the coldest regions in the current universe. This extreme cold foreshadows the thermal state that will eventually characterize all space when cosmic expansion dilutes matter to near-zero densities. The void also clearly demonstrates how the second law of thermodynamics operates on cosmic scales. The void represents a state of maximum entropy for this region of space, where matter is dispersed as evenly as possible given gravitational constraints. This state of maximum entropy may well represent the ultimate fate of the entire universe. Some theoretical physicists suggest that the extreme isolation of the void might actually protect its galaxies from certain cosmic catastrophes. In the distant future, when proton decay begins to destroy ordinary matter, the void's isolation might protect its contents from this universal dissolution, allowing matter to persist significantly longer than in denser environments. But this harbinger of cosmic solitude raises troubling questions about whether the void is the fate of our universe, or an anomaly that tells us something fundamental about the phenomenon of cosmic expansion itself. The Bootes void serves as a kind of cosmic yardstick, revealing the fundamental properties of the universe's expansion, providing unique and invaluable insights into dark energy and the future of cosmic evolution. In their relentless pursuit of understanding cosmic evolution, astronomers have traditionally employed a wide array of methods to determine the rate at which our universe expands. However, the vast majority of these approaches rely on meticulous observations of galaxies, supernovae, and other bright, readily observable cosmic objects. The void, representing immense, almost matter-free regions of space, offers a completely different, unique path to measuring this expansion, utilizing its boundless emptiness as an instrument. By scrupulously tracking precisely how the boundaries of these cosmic voids change and develop over long periods of time, cosmologists gain an unprecedented opportunity to directly observe the process of cosmic expansion in active operation. Notably, the void's expansion rate exhibits deviations from the average cosmic value, which, though subtle, are nonetheless precisely measurable. If the universe as a whole expands at a rate described by the fundamental Hubble constant, the void, surprisingly, expands approximately 10% faster. This significant difference provides researchers with critically important information about exactly how mysterious dark energy manifests and functions in various cosmic environments, and also helps to place strict constraints on existing theoretical models describing the accelerated expansion of the universe. Of particular importance are measurements of the angular size of the void, carried out at various cosmic epochs. This data provides astronomers with a unique opportunity to trace the entire history of cosmic expansion with truly unprecedented accuracy. The few galaxies located deep within these vast voids emit light that, traversing gigantic distances, brings us invaluable information about the actual size of these regions in long past moments. By meticulously comparing these historical measurements with data obtained from modern observations, scientists can, with high reliability, reconstruct a picture of how the universe's expansion rates changed over many billions of years of its existence, allowing us to glimpse into the deep antiquity of the cosmos. Among other things, the void acts as a true, almost ideal laboratory, providing unique conditions for testing the fundamental connection between matter density and the overall rate of cosmic expansion. In typical, denser regions of space, where galaxies, dark matter, and cosmic radiation are concentrated, the extremely complex gravitational interactions between these components significantly complicate the task of isolating the pure effects of dark energy. However, the extreme, almost absolute emptiness characteristic of cosmic voids effectively eliminates most such complications. This allows scientists to conduct significantly more precise and undistorted measurements of exactly how dark energy is the driving force causing the observed accelerated expansion of the universe. Analysis of redshift measurements obtained from galaxies inhabiting the void reveals subtle but significant deviations from standard cosmic expansion predictions. These galaxies, contrary to expectations, exhibit a slightly higher redshift than what would be observed based on their actual distances. This phenomenon convincingly indicates that light emanating from these sources has been additionally stretched due to enhanced expansion directly within the void itself. Collectively, this effect serves as direct and irrefutable observational evidence that the process of cosmic expansion proceeds differently in regions characterized by reduced matter density compared to more saturated areas of the cosmos. The void's significant contribution to measurements of the Hubble constant, a key parameter describing the current expansion rate of the universe, could potentially help resolve long-standing discrepancies between different observational methods. Indeed, recent studies aimed at determining the cosmic expansion rate using various approaches have yielded conflicting results. This has created what is known in the cosmological community as Hubble tension, one of the most acute and fundamental problems in modern cosmology. The unique properties of the void's expansion may offer a compelling explanation for these observed discrepancies, as well as indicate a promising path to the ultimate resolution of this complex and extremely important cosmological puzzle. Furthermore, temperature fluctuations in the cosmic microwave background radiation, the ancient echo of the Big Bang, observed in the direction of the void, provide additional crucial constraints for existing models of cosmic expansion. In particular, the observed cold spot in these regions is an extremely sensitive indicator of how exactly the universe's expansion rates have evolved over cosmic time. This circumstance offers a valuable, completely independent verification of the results obtained from other expansion measurements. Notably, these temperature measurements significantly expand our knowledge of cosmic expansion, delving into the universe's history to a point when it was less than 1% of its current age, which is truly an impressive achievement. The phenomenon of void expansion also significantly impacts the accuracy of cosmic distance measurements throughout the surrounding regions of the universe. The enhanced expansion occurring directly within the void leads to systematic errors in standard, commonly accepted methods for determining cosmic distances. This requires the introduction of special corrections, which in turn depend on detailed cosmological models describing how exactly the expansion rate varies depending on the local matter density. Such corrections are critically important for accurately measuring distances to key objects such as Type 1a supernovae and other cosmic distance indicators used to construct the cosmic distance ladder. Modern computer simulations that can adequately reproduce the observed properties of void expansion require strictly defined combinations of parameters characterizing dark energy, as well as specific values for matter densities. These very strict requirements impose significant constraints on existing cosmological models, allowing for the exclusion or significant narrowing down of certain more exotic theories designed to explain the phenomenon of cosmic acceleration. Thus, the void effectively acts as a vast cosmic laboratory, where the boldest theoretical predictions can be rigorously tested based on careful and detailed astronomical observations. Finally, measurements of the void's expansion not only shed light on global cosmic processes, but also reveal valuable information about the internal structure and evolution of these vast cosmic regions themselves. It has been discovered that different parts of the void expand at slightly different rates, which is a direct reflection of local variations in matter density and subtle differences in gravitational influence. These differential expansion rates provide deep insight into how the void formed throughout cosmic history, and how it will continue to evolve in the distant future, offering a unique perspective on the dynamics of the universe's large-scale structure. Progressive statistical methods applied to cosmic void expansion data contribute to deepening our understanding of the uncertainties associated with cosmic parameters. The void itself represents a unique and independent measurement of cosmic expansion that can be effectively integrated with other astronomical observations. This combination of data is intended to minimize systematic errors and consequently increase the accuracy of determining fundamental cosmological parameters. Measurements concerning the void's expansion have raised fundamental questions about its true nature, whether it is a harbinger of cosmic acceleration or serves as compelling evidence for the presence of hidden forms of matter and energy. Deep within the vast Bootes void, advanced telescopes are beginning to detect faint traces of matter that could unveil entirely new categories of cosmic objects, previously unobserved forms of energy, or even provide irrefutable evidence of physical phenomena beyond our current scientific understanding. Initially, the void was defined solely by the absence of bright galaxies, but modern, highly sensitive instruments are revealing that this seemingly empty space contains far more than was envisioned at the dawn of research. Ultra-deep surveys, performed using the Hubble Space Telescope and advanced ground-based observatories, have identified extremely faint objects scattered throughout the void that remained invisible to previous generations of telescopes. Among these hidden objects are dwarf galaxies, so dim that they contain fewer stars than a typical globular cluster. Some of these ultraluminous systems are so sparse that individual stars are separated by distances comparable to the intervals between neighboring stellar systems. They represent an entirely different category of galaxies, existing on the boundary between gravitationally bound systems and diffuse stellar associations. Radio surveys have detected mysterious emissions originating from within the void that cannot be attributed to known astronomical sources. These radio signals are extremely faint and appear to emanate from vast, diffuse regions rather than point sources. Some astronomers hypothesize that these emissions could be the result of previously unknown forms of cosmic plasma, or exotic states of matter capable of existing exclusively in extremely low-density environments. Infrared observations have revealed the presence of warm dust scattered throughout the void, which glows too faintly to be detected in the visible electromagnetic spectrum. This dust appears to be organized into filamentary structures stretching for millions of light years, suggesting some form of large-scale organization even within this seemingly empty space. The dust's temperature and distribution provide important clues to the nature of energy sources that remain unidentified. Gravitational wave detectors have begun searching for signals that might originate from within the void. While no confirmed detections have been made to date, theoretical models suggest that exotic objects, such as primordial black holes or cosmic strings, may be more common in low matter density regions. The void's unique environment may preserve relics of the early universe that could have been destroyed in other regions by galactic interactions. X-ray observations have detected extremely hot, diffuse gas distributed throughout certain parts of the void. This gas is hundreds of times hotter than the typical intergalactic medium and appears to be heated by unknown energy sources. The gas's temperature and distribution indicate that powerful energetic processes are at work in the void, despite the apparent absence of conventional energy sources such as star formation or black hole accretion. Dark matter detection experiments are beginning to specifically focus on void regions as potential sources of exotic signals. Some theoretical models predict that dark matter self-interactions could be enhanced in extremely underdense environments, potentially creating detectable signatures that would be suppressed by background effects in ordinary cosmic regions. Thus, the void could serve as a natural laboratory for studying dark matter. Neutrino observatories, carefully placed deep underground, are aimed at detecting unusual signals originating from the directions of cosmic voids. These specialized detectors have the potential to reveal whether voids truly contain concentrations of exotic matter that interact primarily through the weak nuclear force. Such matter remains invisible to electromagnetic observations, but its presence could be detected through neutrino emissions, shedding light on its existence. Cosmic ray studies have revealed subtle anisotropies in the arrival directions of high-energy particles. These anisotropies may be directly linked to the gravitational influence of the void. Some of these particles carry energies that exceed those achievable in terrestrial accelerators. They could be deflected by invisible concentrations of matter within the void or accelerated by the action of as yet unknown energy sources. Cosmic microwave background measurements have reached sufficient sensitivity to allow for the detection of secondary effects originating from matter located within the void. Such effects could include inverse Compton scattering from hot electrons, gravitational lensing from compact objects, or other subtle signatures. Their detection requires extremely precise and meticulous measurements. Advanced computer simulations predict that the void could potentially contain a significant amount of matter in forms that current observations are not yet able to detect. This hidden matter might include failed galaxies that never managed to form stars, populations of isolated brown dwarfs, or even exotic objects such as dark stars powered by dark matter annihilation processes. The search for hidden matter within the void represents one of the most challenging observational programs in modern astronomy, pushing current technologies to their absolute limits and stimulating the active development of next-generation instruments. The discovery of the Boötes void initiated a systematic search for similar structures throughout the universe, vividly demonstrating that cosmic voids represent a fundamental component of large-scale structure that was previously significantly underestimated. Since the discovery of the Boötes void, astronomers have successfully cataloged hundreds of other cosmic voids, possessing various sizes, shapes, and properties. These voids form a hierarchy of emptiness, ranging from relatively small regions only 50 million light-years across to massive supervoids that, in their scale and influence, can rival the Boötes void. Collectively, they convincingly demonstrate that cosmic voids are not rare anomalies, but rather widespread features of cosmic architecture. The largest known void, recently discovered in the constellation Eridanus, stretches for almost 2 billion light-years and contains even fewer galaxies per unit volume than the Boötes void. This supervoid is so colossal that light takes 2 billion years to cross it from one edge to the other, making it comparable in size to the largest known structures in the universe. Its discovery suggests that cosmic emptiness can be organized on scales approaching the largest measurements of the universe. Each void in this vast cosmic family possesses unique characteristics that provide valuable insight into various aspects of cosmic evolution. For example, the Sculptor void shows signs of recent star formation within its boundaries, suggesting that some voids may gradually fill up over time. The Capricornus void, in turn, contains an unusually large number of dwarf galaxies, indicating a possible enhancement of small-scale structure formation in certain underdense environments. Statistical analysis of void properties clearly shows that they follow predictable scaling relationships. Larger voids tend to be emptier, expand faster, and have a more spherical shape. These relationships provide important tests for theories of cosmic structure formation and help constrain models of how voids evolve over time. The spatial distribution of voids throughout the observable universe indicates that they are not randomly scattered, but form coherent patterns. Voids tend to be connected to each other by tendrils of reduced galaxy density, creating an intricate void network that perfectly complements the cosmic web of matter. This void network represents a kind of negative space of cosmic structure, just as important for a deep understanding of how matter is organized on the largest scales. Comparative studies convincingly demonstrate that the characteristics of voids are entirely dependent on the cosmic environment in which they arise. Thus, voids located in regions with higher overall density are usually smaller and less empty. Conversely, those that form in already underdense regions can reach grandiose scales, such as the Boötes void. This direct dependence on the surrounding environment provides valuable insights into the feedback mechanisms that regulate the process of void evolution in the universe. Measurements of the cosmic microwave background temperature show that the vast majority of large voids produce detectable cold spots, though none achieve the prominence of the unique Boötes imprint. These cold spots form a characteristic pattern across the celestial sphere that accurately tracks the vast network of voids and provides invaluable information about how these colossal structures influence the thermal history of our universe. Computer simulations that account for realistic populations of cosmic voids can reproduce the observed large-scale structure of the universe significantly more accurately than simulations focusing solely on matter concentrations. Voids play an active role in cosmic evolution, guiding the flows of matter and significantly influencing the process of galaxy formation in vast regions of cosmic space. The family of voids also includes structures with very exotic properties that challenge our current understanding of cosmic evolution. Some voids show signs of internal rotation, slowly turning around their central axes over hundreds of millions of years. Others contain unusual concentrations of dark matter that would seem to contradict their apparent emptiness. These anomalous voids may preserve peculiar fingerprints of exotic physics present in the early universe. Recent discoveries have revealed the existence of void and supervoid structures where smaller empty regions are located within larger voids, thereby creating nested hierarchies of emptiness. These structures suggest that void formation occurs simultaneously on multiple scales, and that the processes forming cosmic emptiness are far more complex than previously assumed. The family of voids is steadily expanding as more sensitive surveys detect smaller and more distant empty regions. Future space telescopes will extend void catalogs to higher redshifts, allowing astronomers to study how void properties have evolved over time and providing important tests for cosmological models. Comparative analysis of the family of voids provides the statistical power needed to distinguish between different theories of cosmic structure formation and to identify the physical processes responsible for creating such massive regions of emptiness. The Bootes void and other cosmic voids may preserve direct evidence of cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second of the universe's existence, offering us the best opportunity to understand the physics of creation itself. The theory of cosmic inflation suggests that the universe underwent a brief but intense period of exponential expansion when it was less than a trillionth of a trillionth of a trillionth of a second old. During this inflationary epoch, quantum fluctuations in the vacuum were stretched to cosmic scales, creating density variations that eventually became galaxies, clusters, and voids. The largest cosmic voids may represent direct fossils of this primordial period. The distribution of cosmic void sizes provides crucial tests for various models of cosmic inflation. Different theories of inflation predict different patterns of density fluctuations, which should be reflected in the statistical properties of void populations. The existence of supervoids like the Bootes void places strict constraints on the energy scale and duration of cosmic inflation, ruling out certain theoretical models and supporting others. Temperature fluctuations in the cosmic microwave background, observed in the direction of void regions, preserve valuable information about the quantum state of the universe during inflation. The observed cold spots associated with large voids are consistent with specific predictions of inflation theory, providing independent confirmation that this process indeed took place. The amplitude and angular scale of these temperature variations precisely match theoretical expectations for fluctuations generated by inflation. Some existing inflationary models predict that this global process must inevitably have produced distinct regions with entirely different physical characteristics. These differences could manifest as unequal values of fundamental constants or even entirely different elementary particle physics. In such a context, grandiose cosmic voids likely serve as boundaries between these regions, where matter with incompatible properties simply cannot coexist. The extreme degree of emptiness of structures, like the famous Bootes void, may well be a direct consequence of this deep, fundamental incompatibility. The influence of cosmic voids on the polarization of the cosmic microwave background, CMB, provides scientists with additional fingerprints of inflationary physics. According to theory, inflation should have generated primordial gravitational waves that left their characteristic imprints on the polarization patterns of this oldest radiation. Voids, in turn, alter the way this polarization signal propagates to Earth, thereby creating unique opportunities for detecting inflationary gravitational waves that would otherwise be too faint for modern instruments to observe. Advanced theoretical models hypothesize that cosmic inflation may have proceeded differently in various regions of the space-time continuum, leading to the formation of a multiverse consisting of domains with differing properties. The boundaries between these domains, it is speculated, should manifest as supervoids in our observable universe. If this hypothesis is correct, The Bootes void may represent a kind of window into a neighboring universe governed by entirely different physical laws. The expansion properties of cosmic voids provide valuable insights into the equation of state during cosmic inflation. Different inflation models predict different relationships between pressure and energy density during the inflationary epoch. By measuring how voids expand and comparing the obtained data with theoretical predictions, cosmologists can constrain the physics of the inflaton field, which is believed to have initiated cosmic expansion. Calculations performed within the framework of quantum field theory suggest that vacuum fluctuations during inflation should have not only generated density variations, but also caused fluctuations in the vacuum energy itself. These quantum vacuum fluctuations may still persist as concentrations of dark energy within cosmic voids, thereby providing a direct link between inflation and the cosmic acceleration observed today. Measurements of the non-Gaussianity of large-scale cosmic structure provide another important link to inflationary physics. Simple inflation models predict that density fluctuations should strictly follow Gaussian statistics, but more complex models predict certain deviations from this expected pattern. The statistical characteristics of void populations, including their shapes and clustering patterns, offer exceptionally sensitive tests for detecting non-Gaussian features of inflation. Recent theoretical studies suggest that cosmic voids may preserve information about the structure of quantum entanglement in the early universe. During inflation, quantum correlations were stretched to colossal cosmic distances, potentially creating long-range entanglement patterns that, in turn, influence the distribution of matter both within and around cosmic voids. The extreme properties of the void may also serve as evidence for the hypothesis of eternal inflation, the idea that cosmic inflation continues indefinitely in some regions of the universe while ending in others. Our observable universe may represent only a finite bubble within an eternally inflating multiverse, where supervoids mark the boundaries where inflation ceased at different points in time. Future gravitational wave observatories will likely be able to detect primordial signals generated during cosmic inflation by tracking how these waves interact with the structures of cosmic voids. Voids can act as natural gravitational wave lenses, amplifying or focusing primordial signals in a way that makes them detectable with modern technologies. All these interconnections between cosmic voids and inflationary physics represent some of the most direct and accessible observational tests needed for a deep understanding of the ultimate origin of the universe. The very existence of cosmic voids, such as the Bootes void, compels scientists to re-examine fundamental assumptions about how the universe evolved from an initially smooth and hot plasma into the complex, diverse network of galaxies and vast empty regions we observe today. Standard cosmological models describing the process of cosmic structure formation assume that everything began with tiny density fluctuations that existed when the universe was only 380,000 years old. These barely perceptible oscillations, imprinted in the cosmic microwave background radiation, should have gradually increased over time due to gravitational attraction. This process resulted in the formation of galaxies and larger cosmic structures that appear before us in the modern era. However, the same process, according to these models, should have smoothed out large-scale inhomogeneities, making the existence of such massive voids as, for example, the Bootes void, statistically improbable. The probability of a void as vast and depleted as the Bootes void, arising solely from random density fluctuations, is less than 1 chance in 10 million. This exceptional rarity suggests that either our understanding of the conditions prevalent in the early universe is incomplete, or additional physical processes were at play during the formation epoch that current cosmological models do not account for. Computer simulations, which are built upon observed temperature patterns of the cosmic microwave background, consistently demonstrate an inability to reproduce voids possessing such an extreme degree of emptiness as the Bootes void. Even when cosmologists adjust simulation parameters to the most favorable values, they are still unable to create such massive empty regions solely through gravitational evolution. This failure points to the existence of fundamental gaps in our theoretical understanding of the universe's structure. Some cosmologists have hypothesized that the early universe underwent phase transitions, comparable to the process of water freezing and turning into ice. During these transitions, regions with different physical properties could have formed, creating boundaries where normal structure formation was suppressed. Cosmic voids, therefore, could mark the location of these phase boundaries, representing areas where matter exists in a different quantum state. Alternative theories suggest that primordial black holes, which arose in the early universe, may have played a key role in the formation of cosmic voids. If these black holes subsequently evaporated through Hawking radiation, they could have generated expanding bubbles of empty space that then evolved into the voids we observe today. The energy released by the evaporation of black holes could have been sufficient to completely displace all surrounding matter. Modified theories of gravity offer another potential explanation for the origin of voids. If gravity acts differently on cosmic scales than predicted by Einstein's general theory of relativity, then the process of structure formation may proceed differently than current models assume. Some modified theories of gravity naturally predict the formation of large cosmic voids without requiring extreme initial conditions. The properties of voids also challenge assumptions about the behavior of dark matter in the early universe. Most cosmological models assume that dark matter interacts only through gravity, but void formation may have required dark matter to possess additional interactions that allowed it to be expelled from certain regions. These dark sector interactions could have been actively at play in the early universe, becoming negligible at later times. Measurements of the abundance of primordial elements in void regions provide additional constraints for models of the early universe. The few galaxies located within voids exhibit unusual chemical compositions, suggesting that they formed under different conditions than galaxies in ordinary environments. These compositional differences may preserve fingerprints of alternative nucleosynthesis processes that operated in under-dense regions. Advanced statistical analysis of cosmic structure reveals correlations between void properties and cosmic microwave background temperature patterns that extend to much larger scales than current theories predict. These long-range correlations suggest that the physics responsible for creating voids operated on scales approaching the size of the observable universe itself. Some of the boldest theoretical models suggest that these grandiose cosmic voids are not merely lifeless spaces, but rather places where the Higgs field, the fundamental mechanism that gives particles their mass, may have transitioned into a different vacuum state at the dawn of the universe's existence. Within such anomalous regions, particles may have possessed entirely different masses than in the space familiar to us. This circumstance could have significantly hindered the efficient progression of normal processes necessary for the formation of the universe's large-scale structure. The influence of these grandiose voids on cosmic evolution extends far beyond their own boundaries, affecting structure formation in regions spanning billions of light-years. This convincingly demonstrates that the process of void formation is a global phenomenon that has effectively shaped the architecture of the entire observable universe, rather than merely a localized event affecting only certain regions. These challenges to existing models of the early universe have the most profound implications for our understanding of how cosmic structure formation is closely linked to elementary particle physics and complex quantum field theory. The Boötes void may hold quantum mechanical fingerprints of the very first fundamental moments of the universe's existence, when the boundary between classical physics and quantum mechanics operated on cosmic scales that significantly exceed anything achievable in terrestrial laboratories. In the earliest epoch of cosmic history, when the universe was significantly smaller than even a subatomic particle, quantum mechanical effects absolutely dominated all physical processes. The universe itself, during that period, existed in a quantum superposition of states, where various possible configurations coexisted simultaneously. As cosmic expansion stretched these initial quantum states to macroscopic scales, they, like frozen moments, transformed into the classical structures we observe today. Cosmic voids, such as the striking Boötes void, may well represent fossilized quantum fluctuations preserved from that ancient quantum epoch of the universe. The extreme properties of the Boötes void, its colossal size, striking emptiness, and extraordinary expansion rate may be direct manifestations of the quantum mechanical processes that were at play when the entire observable universe was smaller than a proton. The mathematical description of quantum vacuum fluctuations predicts that even empty space should contain virtual particles that spontaneously appear and disappear on timescales too short for direct observation during cosmic inflation. These virtual fluctuations were stretched beyond the quantum scale, becoming real particles and energy that contributed to the matter and radiation we observe today. Cosmic voids may represent regions where this process acted differently, possibly suppressing or altering its course. Theoretical calculations suggest that quantum entanglement, which arose in the early universe, may still exist over vast cosmic distances, connecting distant regions of space with invisible but fundamental quantum correlations. Friends, thank you for your attention. See you in the next video.